Yeah. Okay, go on then.
Okay, so slightly ahead of time, we'll come into our first talk. Chris Jennison has impressed me for many years by being stubborn. I approve of stubborn people. And persisting with something that seemed to not be taken up. Designing adaptive trials. I mean, there was a meeting at the RSS. How many years ago was that?
Oh, 89.
No.
Well, there was a meeting in 89,
right.
but which meeting? Oh, John Bassett.
Yeah, but I think it was one 4 or 5 years ago when you and other people talked about designing adaptive trials,
Okay.
and various people got up and said, this is absolutely useless. I work for the pharmaceutical industry. No way are we going to do this because they haven't been approved. and so you do it. Now, in my job in St Andrews, I talk to medics, and I was talking earlier about people doing trials on people in poor countries, and some of my medical colleagues are investigating things like how to cut down TB in parts of Africa. And because they're not working with people who've got a lot of management overheads, they're doing adaptive trials. So I really want to find out more about adaptive design. And so Chris is going to tell us about designing an adaptive trial with treatment selection and a survival endpoint. Over to you.
Thanks, Rosemary. It's very nice to arrive in Cambridge again. I was walking into town last night thinking it's actually pretty much 41 years ago since I arrived, not quite this time, a little bit later in the year, as an undergraduate, coming back once again. And yeah, a lot has happened since then. Trying to get methods taken up, but my co-authors here for part of this work are Martin Jenkins and Andrew Stone from AstraZeneca, so there was definitely an input into this problem. From a trial they were planning to design, that one didn't actually come to fruition, but the methodology came through. There's another trial which I've based this talk around, which is running at the moment. I won't go into much detail about that. That's the title. It's a phase 3 trial design where there are 2 versions of the experimental treatment being considered. And the aim of the trial is to choose one of those and at some point then to focus on that experimental treatment and compare it with control. And as well as choosing one, then you want to hopefully show that that version of the treatment is better than the control. And I think the topic here really allows us to explore a lot of the ideas that are now in vogue in adaptive clinical trial design. There's multiplicity. We've got 2 versions of a new treatment, so there are multiple hypotheses to test. There's adaptation. There'll be 2 phases of the trial, and the second phase will depend on the data in the first phase. So then you have the issue of how to combine data across stages like that when the way the data are collected is itself data dependent. So the methodology, the closed testing procedure for the multiple testing, the combination tests for combining data, I think are the building blocks for an awful lot of different types of modern adaptive designs. We have survival data. The overall endpoint here is, the primary endpoint is overall survival, so we'll have log rank statistics for that. But interestingly, at the interim decision time, there won't be very much overall survival to call on, so that decision will be made on shorter term endpoints. As we approach the topic of the combination test applied to survival data, we'll see that there are some possible pitfalls there, and we have to get around that and find a valid method. That in itself brings us to a certain sort of conclusion, and I have talked about this material basically stopping at that point, and then one time someone asked me, well, and how well does this procedure do? It's valid, it protects type 1 error, but is it actually any good? So I now have more material to try and see if it is any good. And it turns out that's an important question to think about. Okay, so here's the setting, a clinical trial with treatment selection. So imagine, for sake of argument, a cancer trial, a chemotherapy treatment, which can be delivered in 2 different ways. One is, in each cycle of chemotherapy, there's a very intensive short period when the patient is given the appropriate dose, and in the other version of the administration, it takes a little longer. It's a lower dose per day for a few more days. And at the start of the trial, the investigators have an open mind as to which of those two approaches might be better. So this is an opportunity to compare them. And there'll be a control treatment as well for an overall comparison. As I said, the overall survival is the primary endpoint. That's the gold standard in this case. But at the interim analysis, when one is making a final decision about which of the experimental treatments to go forward with, there won't be much overall survival data. There won't be many events. Progression-free survival, there'll be much more information on that. Progression happens sooner. So progression-free survival and safety and possibly some other sort of data, whatever's available, can be used at the interim analysis in choosing which of the two versions of the experimental treatment to go forward with. And after that point, the patients will just be recruited to the selected version of the experimental treatment and the control. So there's the diagram showing this all. Here we have the first part of the study where let's call it the first cohort of subjects being randomly allocated between the two experimental treatments and the control. And at their interim analysis, there's a little bit of overall survival, but mostly progression-free survival, on which to choose a version of treatment. And then in the second stage, more patients are admitted, and they're allocated between this selected version of the experimental treatment and the control. And at the final analysis, we'll have overall survival on all of these. So rather longer follow-up on this first cohort than the second. And it's at this stage we want to do a hypothesis test. Specifically, is the selected treatment better than the control or not in terms of overall survival? So that seems like a nice idea. It's doing what you think was quite natural, to use the data to help run the experiment and put it in the right direction. But how do you deal with things like type 1 error with multiple hypotheses and this fairly complex system, even with flexibility, quite how this decision is made on how to select the treatment? Some of it will be in the hands of a monitoring committee who've got guidelines and then maybe some judgment to be applied. So let's go through the issues in protecting the type 1 error rate. A bit of notation first of all. Let's suppose that we have a proportional hazards model and that in comparing an experimental treatment against the control, there's a hazard ratio, lambda 1 for the first version, lambda 2 for the second, or theta 1 and theta 2 if we take logs. So our null hypothesis, H01, says that experimental treatment 1 is not superior to the control, theta 1 less than or equal to 0. And then the other null hypothesis says that theta 2 is less than or equal to 0. The experimental treatment 2 is not superior. And we'd like to control the family-wise error. So the probability of rejecting any null hypothesis which is actually true should be at most alpha. So there are plenty of methods in the literature on multiple testing for protecting a family-wise error. And a very nice family come from what's called the closed testing procedure. So here are our two hypotheses, H01, H02. In a closed testing procedure, if you want family-wise error alpha, you have to set up a level alpha test for each of those single hypotheses individually, but you also set up a test of the intersection hypothesis that says both of these are true at level alpha. And then the rule is you can reject this first hypothesis, H01, overall, if you manage to reject this simple hypothesis at level alpha and the intersection hypothesis. You can reject H02 overall if you rejected its individual hypothesis and the intersection hypothesis. And this, you can think of this requirement to reject the intersection hypothesis as the way in which we compensate for the multiple testing. Is it obvious that this does control the family-wise error? The trick is to think about which are the true null hypotheses, right? If the true null hypotheses are both H01 and H02, pay attention to the intersection hypothesis. You've got to reject this in order to reject anything. And there's your level alpha test. So there's your maximum alpha probability of making a type 1 error, because you've got to go through that route. If only one of them is true, let's say H01 is true, H02 isn't, well, you've got to reject H01 at level alpha. So again, that's going to control the level alpha overall error rate. And that's the only way to make an error, because that's the only one that's true. This extends to any number of hypotheses, but it's easy to see what's going on with 2. So let's take that as a given. We're going to use a closed testing procedure, and this will protect the family-wise error. Then the other question is, how do we combine data across stages, in particular when the second stage is designed in a way which was guided by data from the first stage? And so the item from the toolbox for this is called the combination test. Suppose, just take any generic null hypothesis. So it could be our H01, our H02, our H0, 12. But in the first stage, we'll get a Z statistic, which is standard normal under H0. Well, that's under the theta equals 0. If theta is strictly negative, it'll be even smaller than that. And after our adaptations, then conditionally on starting things the way we decide to start them in stage 2, we're going to get another statistic Z2 whose conditional distribution is standard normal under theta equals 0. And because it's always got this same conditional distribution regardless of what happens in stage 1, that's also its marginal distribution. And Z2 and Z1 are actually independent. Slightly curious, since the Z2 data are collected in a way which may well depend on Z1, but we've managed to get back to an independent pair of statistics. And so we can combine them, say, in a weighted combination to give a standard normal. These weights could be proportional to the sample sizes in the stages to make this an efficient combination. If you like to think in terms of p-values, then simply convert the z's to p's, and well, you can define things in the same way through the z's, or maybe combine those p's in some other way that you prefer. So that's a combination test. So combination tests, multiple testing procedures, together actually give you all you need to create some very interesting adaptive trial designs. We've got one more complication, though, because we've got survival data. And let's suppose we're going to use a log rank test to do our comparison of one treatment with another. So this could be experimental treatment 1 versus control. The recruitment of patients will be staggered over time. They enter the study when they show up and get randomized. And then each individual can either continue until a death or until censoring. They may be lost to follow-up for some reason. They move away and we don't know what happened to them. At the interim analysis, there's also right censoring simply because we've only been following the subjects so far. So in the first cohort, these subjects who are still alive at the interim analysis will carry on and be followed further later. So we'll get additional follow-up on those. So how do log rank statistics behave? In particular, if you calculate them, say, at the interim analysis and at the final analysis, how do they behave jointly? Well, it turns out they behave very nicely, at least in large sample theory. If we look at the unstandardized log rank statistic, so this is on a scale where, say, the interim analysis S1 is normal with mean, I1 theta 1, variance I1. I1 here is information. It's approximately number of events over 4, but there's a more precise value will come out of the data. That we get from the first analysis. The increment between the first and second analysis is another normal, and it's the same formula but with I2 minus I1 now in place of information. And these increments are independent in large-scale theory. That's been known for a long time. So this brings you back basically to looking at sums of independent normals, just I1 of them to start with and I2 minus I1 of them later. So the survival data doesn't really look any different in this sense from immediate simple responses. So that sounds nice. These are things we can plug into sequential methods quite easily. Yeah. So what if we take these and put them into a combination test? From stage 1 we'll have S1. From stage 2 we'll look at this increment, S2 minus S1. On the Z scale, we've got some Americans here. On the Z scale, right, we simply divide by root I1, root I2 minus I1. Whoops, where's the pointer? And these become our stage 1 and stage 2 Z statistics, so we can put them into a combination test. Everything's fine. Except for one thing. Z2 is meant to be conditionally independent of Z1. And it would be if all we'd learned at stage 1 was the log rank statistic data and nothing else. But Peter Bauer and Martin Posch pointed out some time ago, in practice this condition may fail to hold. Suppose the investigators know more, and in our setup they do know more. They know about progression-free survival on subjects. That's been part of the decision process for choosing which treatment to carry forward. Patients who have not progressed are more likely to live longer. So the progression-free survival, if we look at that and compare the experimental treatment and the control group, it may be a good indicator of how the next contribution to the log rank statistic is going to be behaving. Could you, if you were trying to get a positive result, could you use that to your benefit? Yes, we all know how to cheat, right? You figure it out. If it looks like things are going well on the subjects that we have, we say, well, let's focus on those and let's not recruit many more new ones that might go the other way, and we'll sort of keep that positive looking result. If things aren't looking so good, let's say we have a nice big new cohort in stage 2 that will wash that away and give us another chance to get good results. So you could certainly dream up a way of cheating a bit and not getting the independence property that one needs. And that would lead to a bias and inflation in type 1 error. And that's what Bauer and Posch pointed out. So we're going to have to deal with that. We'll come back to that shortly. Let's just look at the nuts and bolts, though. If we're approaching this combination test, multiple testing procedure with our survival data, what are the ingredients? And what it all really comes down to is a set of Z statistics for each hypothesis and each stage. So we've got the two simple hypotheses and the intersection hypothesis, and then for each of those we've got stage 1 and stage 2. And if we can define all of these, we've got rules for putting them together, although paying some attention to that issue I just raised, making sure we really do have the right conditional independencies that we're going to rely on. So how do we define these? Let's just proceed in a fairly intuitive way. We'll call this method 1. At the first stage, well, it's pretty obvious what to do. You base Z1, 1. So the first one is for stage 1. The second one is treatment 1. On the log rank test of experimental treatment 1 against control. Z1, 2, the experimental treatment 2 against control. And Z1, 1, 2, that's an intersection hypothesis. There's a bit more choice there. One thing you could say, well, is if the intersection is true and we're exactly at theta equals 0 in both cases, theta 1 equals theta 2 equals 0, both treatments have got the same survival distribution. We could pool them. We could do a pooled log rank test of treatments 1 and 2 versus control. That would give us a fairly natural looking statistic. But there are other ways. We could take these individual Z11 and Z12 and combine them through things called Symes test or Dunnett's test. I'll say more later about these. That looks a little less obvious, but there are advantages to doing that in that we'll see that this approach can relate more to the way in which all of the Z statistics are used together in the multiple testing procedure. For now, let's just say there are choices. There are certainly possible ways of doing this. So at the interim analysis, we calculate the first set of 3 Z statistics. Now suppose we select experimental treatment 1, and in stage 2, that's the only treatment we randomize to apart from control. So we can create Z21, a simple log rank test for the second stage cohort, treatment 1 versus control. And testing the intersection hypothesis in the second stage, well, we just have to use that again because we haven't got any experimental treatment 2 subjects. But that's okay because under the intersection hypothesis, H01 is true, and so Z21 by itself already has the right distribution. And if we'd chosen treatment 2 instead, we just do the obvious thing with a 2 instead of a 1. Okay. So we can put all of these things together, and that looks to give us an overall procedure if we follow the rules. So what could go wrong? The problem rises with the situation I described before. If you look at Z21, so this is let's suppose we've selected treatment 1 into stage 2. We're testing treatment 1 against control based on the new data, which is the follow-up on the first cohort and then the new data on the second cohort, comparing that against control. We might have done something, or even just the treatment selection itself, we'll have built this in because we've selected a treatment with good progression-free survival, so that this Z21 is biased. And this is the Bauer and Posch concern actually coming through. And you may look at it and say, well, it's pretty hard for it to have a big effect. But regulators worry about these things. They want you to prove there's absolutely no bias. Right? And you can't, because there is. So that's a concern. Actually, that's the least of our worries. The much more obvious, more blatant place that things go wrong is in the Z212, because we're getting a second stage statistic on this intersection hypothesis using just the same statistic Z21. And this we've certainly chosen because the experimental treatment 1 subjects have got good progression-free survival. We expect to have them, therefore, have them good overall survival. If they're doing better than average on the progression, they'll do better than average on the overall. And so this one really is flawed. This one relies on doing something subtle to sample sizes and things. This one, nothing subtle at all. It's definitely wrong. So that's a problem. We can't follow this approach. The paper I refer to here is in Pharmaceutical Statistics, and I guess my main contribution to it was I heard Martin Jenkins and Andy Stone describing these methods, thinking about the method 1 approach, and I pointed out the problem, although I was only reiterating what Bauer and Posch had said. And Martin Jenkins said, well, we can fix that. What we've done in method 1 is divide things up into what we know at the time of the interim analysis and call that P1 or Z1, and then what we learn after that, and that becomes P2 or Z2. And so this follow-up of the first stage cohort is causing an issue in this Z2 because we know something about it that we shouldn't. What if we just slice through a different way? If we say the P1 and Z1 are just everything that come from the first stage cohort from beginning to end, they're independent subjects from the stage 2 cohort, make Z2 just relate to the stage 2 cohort, then we'll be okay. And that's true. So that's what we propose to do. We do have to be a little bit careful. Even here, just what happens in this red box, how long do we follow the stage 1 cohorts, must be predetermined. It mustn't be a function of their progression-free survival and so on. So if there's any change of sample size or funny business going on, that's an issue. And the referees for this paper, I think there was a regulator in there somewhere, were very specific, and I think very helpful actually in saying you've got to tie down exactly what this Z1 is going to be so that it's predefined before you start the study. It's not data dependent. So we can say we'll follow stage 1 for a fixed time, or we'll follow it to a fixed number of events. you may adapt that slightly to rates of events that are not using anything more informative about progression or survival, but it's basically fixed. And then we get our 3 Z statistics with ones on, stage 1, based on that full stage 1 cohort. And then we get stage 2 statistics, which are completely separate from the new group of subjects. And these we can put together and get a valid procedure. So we've got combination tests, we've got multiple testing, and that will protect the overall family-wise error rate. Okay, so the notes here are really just saying we still have to be careful to make sure that what we do with the stage 1 cohort is predetermined. Because one thing we don't know is at the time of the interim analysis, we don't know what the Z1s are going to turn out to be because they depend on more follow-up data. So if you had in mind a decision rule that had had early stopping maybe at the interim analysis with a positive outcome in mind that assumed you knew these Zs, well, you can't do that. But we're not really expecting that because we're assuming that at the interim analysis we're using progression-free survival because there is very little overall survival. So we wouldn't be in a position to say overall survival was overwhelmingly in favor of one treatment or another. So that's not much of a limitation. Okay. So that gives us our valid method. So that in itself is good. But all we've really shown is that we protect the family-wise error rate. Do we actually have an overall experimental design which is any use? And so I can be virtuous. I can say, well, of course we investigate that. But make the point that there's a fair amount of stuff in the literature on adaptive designs that doesn't get into this second phase of the analysis. It shows that the method works in protecting type 1 error, and one rather assumes, because it seems to be doing nice things, it must be an improvement on what you would have done otherwise. And sometimes it is, but sometimes it isn't. So what should we compare with? Well, a design which is much simpler to deal with is just one that has the 2 experimental treatments in the control, and it follows them all the way through. So the randomization is between the 3 treatments right through the trial. There's no interim treatment selection. And there's a final analysis which compares both treatments against control. So with control for multiple testing, but we know how to do that. So how much are we gaining by using the data to cut out one of these treatments at a midpoint? Particularly bearing in mind that we're doing it on data on a different endpoint, which we hope is a good indicator of the real endpoint. But maybe it's not so good. And maybe there's not so much data. So does this help? So I just set up a simple scenario, keeping everything as simple as possible. Although we've got survival data in the background, I said, well, it's the overall test statistics that come out of that for which we have normal approximations. So I'm just going to work with the normal approximations. So these simulations don't actually work with survival data, they look at the summary statistics. And my models really are just a way of getting a set of conditions, a joint distribution then, for these summary statistics. So I've said for overall survival, well, we've already got this in the model, we'll have constant hazard ratio, and it's θ1 for treatment 1 versus control, θ2 for treatment 2 versus control. And these 2 statistics will be correlated because they've got a common control arm. We can work out what the correlation is. Again, from the large sample theory, it's basically a half. What about progression-free survival? Well, that's another time to event. Let's suppose, for simplicity, that also follows proportional hazard model for each treatment versus control. But these parameters, psi1 and psi2, may not be the same as θ1 and θ2. But they're certainly related events, so each pair of statistics, the 2 involving treatment 1, will have a correlation rho, say, and then the pair involving treatment 2, they have the same correlation rho. So that's a pretty simple setup. It's actually, I think, possibly really not possible to have this as an overall model. Can you really have proportional hazards on the first event and then the later event? Well, you can get pretty close, but I think it's probably not quite right. But it doesn't really matter, because all I really want to say is when I get my 4 different test statistics at the interim and at the final analysis of progression-free survival, overall survival, I've got certain means and variances and correlation. And the ones that come out of this are the ones I'm using. And if you don't like those, you can change them a bit. But this seemed a nice place to start. Now, what else should we say? We don't want to have too many parameters. So let's suppose that there's a simple relationship between the hazard ratios for overall survival, progression-free survival. And that is that one is gamma times the other. So the hazard ratio for progression is gamma times the hazard ratio for overall survival. So gamma will be an important number. And then there's not much loss of generality in really just putting in overall numbers to show what scale we're working on, what kind of power we're going to have. Let's suppose that the overall survival events for the stage 1 cohort at the end, when we're looking at the final analysis and getting the Z1 from stage 1, there'll be 300 events. And that's over 3 treatment arms, of course, equally randomized. They all get followed up. Even though we drop treatment 1 or 2 at the end of analysis, we follow all those patients. We're assuming it's not the sort of treatment where you'd want to go back and switch patients around. The stage 2 cohort, I'm also supposing that gives a total of 300 events. Given the shorter follow-up, that must mean there's a bigger recruitment to make that work out. And that's over just 2 treatment arms in the adaptive design, but it will be 3 in the non-adaptive approach. Of course, we don't really distinguish between the cohorts in that case. Just lump them all together. And the number of progression-free survival events at the interim analysis, well, I wanted to look at everything relative to this same number, 300, so that's going to be lambda times that. And it depends very much then on how rapidly survival and progression-free survival are related as to whether lambda is big or small. Okay. The large sample theory tells us all the distributional properties of these things. So we can simulate and apply the different tests that we're interested in just by generating various normal random variables. So one question is to go back and say, well, there was this issue of how to test the intersection hypothesis. And I mentioned it may seem quite natural to do it by pooling the 2 experimental treatments and comparing them with control with a pooled log rank test. So that's one option. But given this is going into a procedure with a closed testing procedure, one may do better to pool in a different way. So Symes' test and Dunnett's test, you can think of as operating on the 2 p-values for the individual hypotheses. So this is all based on the stage 1 group, let's say for ease of thought. So we've got our normal deviates, or we've got our p-values instead. They're simply related. In Symes' test, if you have a p1 and a p2 for a pair of hypotheses, you test the intersection by taking twice the minimum, which is a Bonferroni type of adjustment. But also, that will be slightly conservative on its own. If the maximum of the 2 is smaller, then you can use that one. So that's the formula for it. And that will protect the type 1 error in this intersection hypothesis test, still a little bit conservatively, as long as these p's are independent or positively associated, but they are positively associated for us because there's a common control arm. Dunnett's test is designed specifically for comparing several treatments with a control, so that seems quite apposite here. And you simply look at the maximum of your z's or the minimum of your p's, and you work out what it would look like under the global null hypothesis and just get the p-value from the distribution of that statistic. So the Z1 and Z2 would be bivariate normal, and because of the common control, have a correlation of a half. So we can find that instead. So here's my particular setup. First of all, just in looking at this intersection hypothesis and how to deal with it, I'm going to suppose that my hazard ratios are actually the same for overall and progression-free survival, just for now. I'm putting a correlation between the two statistics of 0.6. And what am I interested in? Well, it's an interesting question in itself. We really want to select the better treatment, and we'd like to show that it's better than the control. But if we select the second best treatment and still show it's better than the control, that's worth something. So we'd like, my theta 1 will always be bigger than my theta 2. So P1 is most important, and then P2 is the probability of getting a second prize. And you might say, well, there's a gain function. If you're a company with a new drug, how would you combine that? Well, I said, let's weight these events by the treatment effect. So you get a better return on approving a drug that has a bigger treatment effect. So I simply weight the two treatments by the hazard ratio of treatment versus control, theta 1 or theta 2. So that's a possible utility in the overall scheme of things. Again, you could come back and tweak that and do other things with it, but it seems a very simple, direct way of combining the different ingredients. So the first comparison is to say, let's look at these tests of intersection hypothesis. So we've got the Poole's test, the Symes test, and the Dunnett's test. And if you look in terms of P1, what's the probability of choosing the better treatment and getting a positive result for it? We get these set of numbers. And the Dunnett is ahead each time, or else there's pretty much a tie at the bottom. But there's no reason not to prefer the Dunnett test. And in terms of the expected gain, where we're multiplying this probability by, or P2 by the associated effect size, we also find that the Dunnett test wins out. Slightly behind in that box, but we'll say on balance Dunnett is winning. Okay, so that cuts down the options. We'll just use the Dunnett test from now on. And now we'll do the real comparison, which is against the non-adaptive design. Right? What about the very simple design where we have all three treatments, two experimental and control, all the way through? And we'll do a closed testing procedure at the end. Because in this case, we can reject both null hypotheses, because they're both on the go at the end. In which case, we have to say, well, which treatment do we actually choose and imagine the company takes to market? Well, I would say it's the one with the higher estimated effect. So if H01 is rejected and theta hat 1 is greater than theta hat 2, we call that a P1, and the other way around it's a P2, and we've got the same formula for expected gain. So now we can draw some comparisons. So this is the same setup as before, that the overall survival and progression-free survival have the same hazard ratio. So gamma equals 1 in there. Lambda equals 1, that was to do with how much information there is on progression-free survival at the interim analysis. I've said it's the same as the information on overall survival. And I've now got a variety of theta 1s and theta 2s. So these are the hazard ratio between an experimental treatment and the control. So in the first couple of cases, treatment 1 is clearly ahead, and at the end they're almost indistinguishable. And what we see is that the adaptive procedure is better at choosing the better treatment, well, until they get very close. And actually the non-adaptive procedure has an advantage now, because it's keeping both treatments right through to the end. So it has more information to make a better decision. But the adaptive procedure still wins out overall when we look at the other option of choosing the other treatment and getting a positive result and combining that into a gain function. So these blue numbers in the final column are better than the red numbers in the final column. So adaptivity has helped. Has it helped enough? In terms of gain, we're up about 10%, but we've had to run a more complex design. Well, that's a matter of judgment now. It's, how much did it cost you to do this more complicated design? Of course, this is only one situation where lambda is one, but gamma is one. What is this gamma? The treatment effect that you see in overall survival, which is what you're really interested in, compared to the treatment effect you see in the shorter-term endpoint, progression-free survival. My first thought on that was, if you look at the wrong endpoint, well, you might be misled. So maybe we should think about situations where we don't see such a big treatment effect on progression as we do on survival. But actually, you could turn it around. Imagine you're following a study and you're hoping to see an effect on overall survival, and you've got to the stage we've got lots of progression data, and you say, we've got a good effect on progression. Will we see that in overall survival? Quite often, that effect gets diluted. There's more things that can happen, and you're getting later on from the initial treatment. So it's not unusual to have a larger effect on progression than you do or have on overall survival, which is actually good news here. That says that what we'll see at the progression stage when we're choosing a treatment will be very good information to choose the right one. And it's just hard work to prove that it was good on overall survival later. So that's the argument that says gamma, my ratio here, could be greater than 1, which will be helpful. So I'm now just going through the same sort of calculations, but varying gamma. I fixed a few other things. I fixed the hazard ratios of 0.3 and 0.1 on overall survival. And as you move up and down the table, at the top end, we've got gamma and lambda both bigger than 1, which means we're getting more progression-free survival events, and they're very informative about overall survival. And so our probabilities of making a good decision there go up. So we're definitely better off. And so this expected gain up here, 0.264 versus 0.234, that's now really looking a bit more worthwhile. If, on the other hand, things actually go the other way, and I've kept lambda and gamma equal, but you can have differences between them, you might have a good gamma, so progression-free survival is very helpful, but you've timed your interim analysis and your decision point when you don't even have many progression events. And then you really don't make the right choice. Well, down here, you can be worse off than if you'd just done the non-adaptive thing and gone through to the end. So the point is that adaptation can be helpful as long as you've got good information. You could have said this before we started, right? To make the interim decision at the time that you need it. But we've quantified all of that now. In fact, one might look at other things at the interim analysis. Pharmacokinetic data. How are these drugs being taken up in the body? And if you don't see good results there, then you'd be very suspicious about anything else you see about progression and survival in the interim data. I think the other good thing to say, at least comparing this design with a design where you just choose one of the treatments before you start, is to say you are at least learning about these two different ways of the drug delivery in a properly controlled large study. Of course, you get that both in the adaptive and non-adaptive examples that I've shown. So that pretty much wraps things up. There are a couple of things to point out. In parallel to that paper with Stone and Jenkins, there's a paper by Earl and Schaefer in JASA, came out about a year later, where they also addressed this problem of combination tests or equivalence to a combination test for survival data. They use the conditional probability of rejection principle. So those who know what that is will know what it is. I think it's actually rather hard to work with, in my view, because you've got to be able to predict how much data you would have had at the stage that you didn't move on to in order to use it. I think combination tests sort of cut through that and keep life a lot simpler. So that's why we recommend it. There's a nice paper by Frieda et al. Looking at a very similar sort of situation in a phase 2/3 trial, so that's treatment selection and testing, not with survival, but with longitudinal data on the endpoint. So you've got a long-term endpoint and a short-term endpoint. And again, they used a similar approach to have the same problem there about the short-term endpoint being informative about the long-term endpoint. So they solve the same sort of problem in the same sort of way. So my conclusions are, one can have adaptive trials with survival endpoints and treatment selection and everything. And I hope if you're not familiar with this area, you've seen these basic tools of combination tests and multiple testing working together. Basically very simple construction, but as soon as you get these longitudinal event data, there are the complexities that one has to be careful with. And the end result looks to be a valid and potentially efficient overall procedure. Thank you.
Thank you very much for that. Does anyone have any questions or comments?
In these combination tests, you're reducing the data essentially to the p-value, right?
Yes?
Short of being a sufficient statistic, we're going to lose some information. Do you have a good feeling how much or how important it is?
So within each stage, you'll be using a sufficient statistic, but when you combine them, you may not have an overall sufficient statistic.
The p-value is not necessarily a sufficient statistic, right?
Well, I would say the way you get to a p-value is by doing the standard test that you would do within that stage of the data. So I would expect that to be based on sufficient statistics, and you make that as, if you like, the best p-value that you can. So the one that's got the right null distribution and is skewed in the right direction as much as possible when the null hypothesis isn't true. So I don't think that's an issue. I think when you put things in a combination test, there can be an issue. If you have to pre-specify the weights, if you're doing the weighted normal test that I described, it would be another setting really where you might find your second stage sample size was being varied according to the decision that you make at the interim analysis, and yet the weights have to remain fixed. And so then you find that you're combining X bar and Y bar, but not in the way that you would do if it was just a pooled sample. So you lose a little, but it's a price that one has to pay to protect the type 1 error, at least by this sort of machinery, in a way that is robust to other aspects. And it gives you the freedom to do a lot of other things, basically.
Francois.
Yes.
Did you study what happened if, at the end of the first cohort, you decide to keep the two treatments because there is not enough difference between the two? Do you always have to make a decision?
In my setup, I always made a decision.
Even if the two
what
are
if they're
very
very
close,
close?
or the two, theta 1 and theta hat. Theta
Well,
1.
it depends. Are you trying to find the best one, or are you trying to find one that works? So you could say if they're that close, it doesn't matter. You can just choose either. So I don't think it's a problem. But you might say if you really wanted to know which of those delivery methods was better, you'd rather carry on with both.
And the other question, can you stop at the end of the first cohort if you have no effect at all? Can you decide?
Well, you can certainly stop for futility and just give up. What you can't really do is make some allowance for that in saying that must have avoided some routes to a false positive, and I'll put that back in later because I don't think we have enough information about all the data that's being used there.
Vlad?
I think that in practice, in industry, this type of designs are called seamless phase 2/3, and that is telling you what was the reason for considering this. This is just to bring efficiency in drug development by combining these two phases in one. And I think that I didn't see in your evaluation or comparing the operating characteristics exactly that element. So an idea was, instead of running a phase 2 with 2 treatment and placebo or control, select a dose and start again with that selected dose and placebo, combining them together is bringing you efficiency. So you picked in your comparison, let's say, interim analysis is exactly when half of the information is from this one. In practice, we don't do half. We do 1/4, 1/3. And I'm not sure if your conclusion will remain true, if that will be the scenario, how you compare. And you didn't say anything about savings in total number of subjects.
Yeah. So phase 2, 3, you're right. You're probably aware, I've looked at that somehow in quite a different way. I was thinking about that on the train on the way here. Why am I thinking of these as two different problems? It's partly a matter of what you call phase 2, phase 2B, and I think the world is changing. You know, it's just not such a simple distinction. Because in the cancer trial, there isn't so much a phase 2; it's almost phase 1. The tolerance is the issue. The dose level is the maximum that patients can tolerate, and that's what you're looking for. So here, the method of delivery was a slightly different. But you could say, well, that's something we should test in phase 2 first. So yes, if we'd made a comparison to say, what about the trial that does the first half and then stops and loses all that data and then starts all over again, well, clearly we should be doing a lot better because we're using the extra data. Now, in the context of more things that would be called phase 2, 3, Lisa Hampson and I have explored that in some depth to try and work out how much do you gain from using the phase 2 data in phase 3. They get some kind of adjustment for multiple testing and so on and so on. You even have to work out, well, how do you combine them? There are so many different routes to doing that. And the very simple summary that we felt is a rough guide is that the phase 2 data on the treatment that you select and the control, when you put them in phase 3, they're about the same value as having 50% of those numbers straight into phase 3 without all the baggage of coming from phase 2. So that's clearly a good, worthwhile activity. But where should the interim analysis be? Should it be the halfway point? When I said halfway, I mean it's really driven, in my example, by the time it takes to get the right number of progression events. And as the slide was showing you, if you don't have enough progression events, and you're down here somewhere, so that would be lambda being less than 1. I've also changed gamma at the same time, but they kind of function separately from each other. If you make that decision too early, then you'll make the wrong choice a lot of the time, and you won't be doing very well. So that really depends, I think, on the whole issue of how all the different ingredients, survival, progression, recruitment, follow together, and I'm sure some planning and thinking. As sometimes you feel you want recruitment to be slower in order to have more time to look at the patients you've got before, and that's true for any adaptive setting. So that's quite a complicated issue, and one could certainly try and fine-tune it.
Did you have another thing? Yeah.
Chris, many thanks for your very interesting presentation. If I understood you correctly, the simulations were based on the normal approximation.
Yes.
But in real life, you have survival data, and you said for a strict abnormal control, you have to fix the number of events per stage as a p-value, which means usually you would not expect that at the same time point you reach the number of events needed for both stages at the same time, which means also for your method you cannot use all the data available.
Mm-hmm.
When you had this discussion with this company, you were disappointed that it might be the case that not all survival data can be used, because then usually the long-term survival data most likely are the ones which can be used, because just for the abnormal control it's somehow still unnatural that not all data can be used for final decision making.
Yeah. No, you're right. It's an awkward sort of restriction that says, in order to keep this Z1, this P1 to mean what it was meant to mean, we've got to tie it down. Even though we've ended up getting more data than we thought, we have to ignore some of it. I did say, though, you could have a fixed time at which you do the final analysis, and you get the same asymptotic theory applying. So you don't have to have a fixed number of events, you just have to have a fixed something. So the information would then become random, but your Z would still have the right distribution in large samples. So if you're able to fix times, that might be okay. However, what you probably find is that when your second stage cohort is being followed, events come a little less quickly, you decide to keep going longer, and now you're not allowed to keep the first stage data from the extra follow-up. So this can definitely happen. Trying to work out, have you looked at this? This rings a bell. How do you use the follow-up data?
We tried to adjust the critical value, like a worst case adjustment, but this is so inefficient, that's also not the way to go forward.
Right, okay. So if it wasn't for this type 1 error thing, we could, could use the data much better.
I think
Very last one. And which hazard ratio would you report at the end of the day?
Which hazard ratio?
Use the data, or how would you proceed?
So, I haven't really thought about that. So for the testing, we're obliged to put the two pieces together. For consistency with that, it would seem it would make sense to do the same thing, do something parallel, but I don't know what happens. If you just pool the data and say that's a point estimate that presumably has potential bias, you then have to go down the route of adjusting the bias, but that might be a better place to start.
I'm sorry, I think we will have to call a stop now so that there's time for the coffee break. There's plenty of time during the week for discussion. Thank you so much.
Thank you.